Hello. In this presentation, we are going to present our project for the machine learning course on deep reinforcement learning-based scheduling for electric vehicle charging. In this project, we have designed and implemented a deep reinforcement learning framework that helps scheduling of electric vehicle charging and discharging operations at a parking lot. The main goals are to make sure vehicles are charged before they leave, minimize costs, protect the transformer, and handle unpredictable behaviors like vehicles showing up at random times or electricity prices changing. EVs are changing transportation, but when a lot of them show up at the charging station to charge at the same time, it can cause problems for parking lots.
Managing electric vehicles charging is not easy and has several challenges. EVs arrive and leave at random times, and each one needs a different amount of charge. Some are almost full, others are nearly empty. And on top of that, electricity prices change during the day, so charging at the wrong time can cost money too. If too many vehicles charge at once and simultaneously, it can overload transformers and cause high energy use. That's why it's important to have a smart way to handle charging.
Rule-based or static methods are not capable of handling the complexity of modern EV charging systems. They can't keep up with all the changes, like EVs coming and going at different times, dynamic electricity pricing, or limits on the power grid. That's why we need a smart system that can learn from what's happening and make better decisions as things change. And figuring out when to charge or discharge EVs is a step-by-step or sequential decision process with uncertainty. DeepQ networks learn optimal charging and discharging actions by interacting with the environment and receiving rewards or penalties. Over time, the system learns to adjust based on things like EV states, how electricity prices change, and any limits on the transformer. The agent's core decision making is a DeepQ network defined in the DQN class. The network architecture consists of 4 input layers and 3 hidden layers. The first and second hidden layers each contain 128 neurons, while the third hidden layer contains 64 neurons. After each layer, there is a ReLU function to ensure non-linearity and help the network handle complex patterns. To avoid overfitting, it also uses dropout layers with a dropout probability of 0.2 after the first and second hidden layers. In the end, the network gives 3 possible choices, one for each action it can take: charge, discharge, and delay. Here you can see the code we have written to implement the architecture I have explained earlier in the previous slide.
The agent is trained using the Adam optimizer. The learning rate is slowly reduced over time using something called step RL scheduler. The loss function is mean square error between predicted and target Q values. And to keep the training stable, it limits how big the updates can be by using gradient clipping with a max value of 1 during backpropagation. In this Python code, you can see that the loss function is set to be mean square error, and we are using the Adam optimizer. The DQN agent has some key features to help it learn better. It keeps a memory of past experiences and randomly picks from them during training, so it doesn't learn just from recent events. It chooses actions using a method called epsilon greedy. This means sometimes it tries new things and sometimes it sticks to what it has learned before, with a shift over time toward using what it knows works best. During training, the agent predicts current and target Q values, minimizes the loss, and updates model weights. It also uses two versions of the network, a main one and a target one, which it syncs periodically to keep things stable. Plus, it can save and reload its progress anytime, which is great for continuing training or using the model later. In this slide, you can see the implementation of DQ and agent functionality that we have written based on my explanation.
The scheduling environment is set up as a Markovian decision process where the agent keeps an eye on what's happening, takes action, and learns from the results. It has three actions: start charging, which is +1, start discharging, which is -1, or delaying action, 0. The goal is to find the best way to act over time so it can earn the most rewards by making smart decisions based on the interaction with its environment. Each EV is characterized by a dynamic state vector, four changing details. 1. How full the battery is, which is state of charge. How much more time it needs to charge. How long it will stay parked. And what hour it shows up. The agent is trained to learn the best way to handle EV charging requests. It tries to charge EVs when electricity is cheaper, sell back power during expensive times if it makes sense, and avoid overloading transformers. This helps save money and keeps the power system running smoothly. The system gets rewards and penalties based on how well its choices match the goals. It gets points for charging EVs that have a low SOC, for discharging when an EV has enough charge, and for waiting if there's still time to charge later. But it gets penalties if it overloads the system, lets the vehicle leave without enough charge, or discharges a vehicle with too little battery. This design helps the system learn to keep users satisfied, save money, and protect their power grid.
We define a function called generate daily EV distribution to model the stochastic arrival of EVs during the day. It follows hourly probability distribution patterns with more EVs arriving in the morning and evening, just like people commuting. When an EV arrives, it gets a random battery level between 20% and 90%, a charging time it needs, and a parking duration that gives enough time to charge, but still feels realistic. Training happens through a function called train model, which simulates a full day, 24 hours at the parking lot. At the start of every hour, it checks how many new EVs have arrived based on the hourly pattern. It gives each new EV its battery level, charging need, and parking time. Then it updates all the active EVs and sends their info to the agent. For each group of EVs, it chooses actions using ActBatch method. It then figures out the rewards using calculate reward batch function based on things like electricity prices, how much charge the EVs need, if discharging is possible, and whether the system is being overloaded. These rewards help the agent learn what choices work best. Here you can see the code to update charging and discharging amounts plus transformer power in case of different actions. The way rewards are set up helps teach the agent what to do. It gets encouraged to wait when there is still plenty of time left to charge. It's pushed to charge EVs with low battery first and get extra points when an EV is almost fully charged. Discharging is rewarded if the battery is more than half full, so the EV can help the grid without running low. But if the system uses too much power, more than 90% of what the transformer can handle, it gets penalties to prevent overloading the grid. The agent stores transitions in its replay memory and updates its policy through the replay method. It randomly picks small groups of them to train on, which helps it learn more steadily. In each training step, it compares current Q values and target Q values, and the difference is backpropagated to update the model parameters. To keep things stable, the target network is periodically synchronized with the primary model.
Evaluate and see how well the model works. It is tested using the test model function. During testing, the agent epsilon is set to be 0.01, which means it mostly sticks to what it has learned, only trying new things 1% of the times. Each test simulates a full 24-hour cycle, which with EVs arriving at random times and dynamic electricity prices. Performance metrics, including total rewards, average SOC, charging and discharging counts, and transformer load profiles, are collected and analyzed. After testing, the whole model, including the primary and target versions, the optimizer settings, and the current epsilon value, is saved. This makes it easy to reuse the model later or continue training if needed. This figure illustrates the DQN framework used in our project, as we explained earlier. The agent interacts with the charging station environment by selecting actions based on Q value, which is predicted by deep neural network. EV requests are processed and state transitions are stored in a replay buffer for training. The model is updated using sampled experiences with a target network which is ensuring stable training. During training, the agent deals with a stochastic environment. EVs show up with different battery levels and parking types, and electricity prices keep changing. After about 2,000 training episodes, the agent gets better and better at making smart choices, which you can see in the improvement of the tracked results. The figures give a good look at how well the training went. The loss curve shows that the model quickly learned and then stayed pretty steady after about 2,000 training episodes, which means it got really good at making accurate predictions by estimating a reliable Q values. At the same time, the epsilon value slowly dropped, showing that the agent moved from trying out new things to mostly using what it had learned. In the bottom figure, you can see total rewards going up with each episode and then leveling off. That's a great sign. It means the agent kept getting better at making smart decisions and eventually found a reliable way to handle both local and overall goals in the system.
Figure 4a shows how the transformer load changes over time during training. At first, there are a lot of inflections or fluctuations because the agent is still exploring and figuring things out. But as training goes on, the load becomes more stable, showing that the agent learns how to avoid overloading the system and manage energy use better. Now, figure 4b supports this by showing the average load for each hour. The numbers stay safely below the transformer's threshold, which means the agent is making smart, load-aware decisions as it learns. Figure 4c shows how the average battery level, state of charge, changes during the training episodes. Over time, the agent learns how to keep it steady between 65 and 70%. That's a sweet spot. It means most EVs leave with enough charge without wasting energy by overcharging. This shows that the agent is doing a good job at balancing what the user needs, running the system efficiently. Figures 4D and 4E show how often the system charges and discharges the EV during training. As the agent learns, both actions happen more often but also become more organized. Charging mostly happens when the lots of EVs are around, and discharging is done at times when it actually helps reduce the stress of the system. This shows that the agent isn't just using discharging to send power back, it's using it smartly to keep the grid balanced during busy times.
The trained DQN agent was evaluated and tested over 100 episodes, with each test simulating a full 24-hour day. During this test, electricity prices changed and EVs showed up at random times, just like in real life. These figures show the performance indicators of how well the agent performed and how steady and effective its decisions were. The figure on top left shows how many rewards the agent earned in each test episode. Most of the time, it scores between 35 and 50, which means it's making smart choices that balance cost, user satisfaction, and the system constraints. Some reward drops happen because of random changes in EV arrivals or electricity prices, but overall the results are solid and consistent. The figure on the top right shows the average battery of all EVs at the end of each episode. This chart tracks the average battery level, state of charge of all EVs at the end of each episode. The numbers mostly stay between 65% and 70%, which is great. It means most vehicles leave with enough charge without wasting extra energy. It shows that the agent keeps things efficient. The figure in the bottom left shows the number of charging and discharging actions per episode. Charging usually happens between 200 and 240 times per episode, which matches how many EVs show up and their energy needs. Discharging happens 80 to 120 times and is used regularly. This shows the agent has learned to use discharging smartly, mainly during busy times or when electricity is expensive, without letting EV batteries get too low. The figure in bottom right shows how much power was being used every hour during the last test episode. The load stays well within the limits of what the transformer can handle all day long. There is a clear peak around noon, but the agent handles it well, keeping everything under control. This proves the agent can play its actions in a way that avoids overloading the system. This group of charts gives a detailed look at how the system and the agent behave over a full day during one test episode. About EV presence, the bar chart shows when 80 EVs are at the parking lot over 24 hours. Most EVs show up in the early morning and leave by late afternoon or evening. Peaks are around 7 to 9 a.m. and 4 to 6 p.m., which match typical commuting hours. And this means the simulation does a good job mimicking real-world arrival patterns. And about setup charge levels, the heat map shows each EV's battery level during the day. Darker green means higher SOC levels. You can see what most EVs start charging soon after they arrive, and their battery levels go up over time. The agent avoids overcharging and keeps most EVs in a healthy battery range, usually between 50% and 90%.
The plot regarding the charging actions shows that and maps each EV's action over time. Green squares mean charging, red means it's discharging, and gray means it's not doing anything. The agent charges EVs shortly after they arrive and uses discharging carefully, mostly during peak hours or when an EV's battery is pretty full. Uh, the bottom graph shows hourly behavior. Green bars show how many charging actions were taken per hour. Red bars show discharging actions per hour. And the blue line shows how much power a system is using, I mean transformer load, which stays well below the capacity threshold even during peak hours. There is a big spike around hour 8 when lots of EVs are present. But even then, the load stays under the red dash line, which marks the safety limit. This means the agent is handling high demand times well without overloading the system. Here, you can see the code we have written for testing a single episode with a heat map for one full 24-hour test episode. This project shows that deep reinforcement learning can do a great job managing EV charging. Even when things are unpredictable, the trained agent finds a good balance between saving energy, protecting the power grid, and user satisfaction. It makes smart, flexible decisions based on what's happening in real time, like how many EVs are there and what's electricity costs. These results prove that deep reinforcement learning can be a powerful and scalable tool for today's energy system, helping build smarter transportation and more sustainable cities.
While this TQN-based framework does a good job of managing EV charging at one station, it does have some limits. Right now, it only works for a single location and uses fixed patterns for when EVs arrive and what electricity costs. In the future, the plan is to build a smarter, more flexible models that can handle real-world uncertainties better. This includes using multiple agents to manage different stations, adding prediction tools, and bringing in renewable energy and storage systems. All of this will help make EV charging more scalable, efficient, and sustainable. Thank you for your attention.